In today's class, we will discuss about dimensions. Dimensions is nothing but the power of the fundamental units in terms of which a physical quantities can be represented is known as dimension. So dimension is nothing but it is the power of the fundamental units that is represented for a physical quantity. Is called as dimension. So we will take an example, area. So we know for area we have the dimensions only in length, and area we will be having it as length square. So if you see the power of the fundamental unit is the length. So we have discussed the fundamental and derived units and SI units also in our previous lessons. If you have any doubts, you can watch those videos. So for area we have length and it has length square. So this is called as a dimension. We will see some other examples like velocity. So for velocity we know the formula is displacement by time, and for I will write displacement by time, and for displacement the unit is L, and for time it is T. So it is L by T. If you look carefully, length is a fundamental quantity and time is also a fundamental quantity. The next example we can take is acceleration, and the formula for acceleration is velocity by time taken, and we know the dimension of velocity, which is length by time divided by time, and this can be written as L by T square or L T power minus 2, because we have the T term in the denominator which has the power 2. If it comes to the numerator part, it becomes as negative. So LT power minus 2. So dimension is nothing but the power of the fundamental units which is used to denote the physical quantities is called as dimensions. Okay, now we will see some examples or how to solve this dimensions. We will move on to another example, which is force. Force the formula for force is mass times acceleration. So mass is written as m, and for acceleration we found out which is L T power minus 2. So the dimension for force is ml t power minus 2. Moving on to pressure. The formula for pressure is force by area. So we will be having this. For force we have ml t power minus 2 divided by, for area we found out which is L square. So which is, when we cancel this L and L, we will be getting m t power minus 2 in the numerator and one L term in the denominator, which can be written as m L power minus 1 t power minus 2. Now this is the dimension for pressure. So we have seen some examples for the dimensions. Now we will try to solve a problem using this dimension. The problem is V square is equal to V naught square plus 2as. V square is equal to V naught square plus 2as. We have to check whether the dimensions of left hand side and the right hand side are equal. So first we will check for LHS, left hand side. In LHS we have V square. Here V is velocity, so we know the dimension of velocity is L by T. And since we have square, we have to square the term. The final answer is L square by T square. Now this is our LHS term. Now for RHS, we have actually two terms. The first one is V naught square and the second one is 2as. So we have to check whether the dimension of V naught square and 2as are both equal. So for V naught square, since it is also velocity, we will have the same dimension, and since it is square, we can write L square by T square. Now plus 2 is a numerical constant and it has no dimension. Numbers usually don't have any dimensions. So for acceleration we know it is L t power minus 2 for acceleration, and for S, which is distance or displacement, we got length. So if you look carefully, means L and it is in multiplication, so it can be written as L into L is L square. Okay, so we have L square by T square for V naught square plus this L t power minus 2 can be written as L by T square into L, so it is L square. Now if you look carefully, both the dimensions are same. So this is 2 and this is 1. Both 1 and 2. If you compare the LHS and RHS, we have L square by T square which is equal to L square by T square. So from 1 and 2, both LHS and RHS are same. So the dimensions are correct, which means the formula is correct. Formula is valid. V square is equal to V naught square plus 2AS. Now we will see, by using dimensional analysis, what are the uses of using dimensional analysis. Uses. The first one is to test the correctness of the equation. To test the correctness of the equation. And the second one is to derive the equation. To derive the equation. And the third one is to convert one system of unit into another. One system of unit into another. So these are the uses of using dimensions. In the previous example, we have seen like how dimensions is used to test the correctness of the equation. So we have seen the correctness of this equation, and it is also used to derive the equation, and it is used to convert one system of unit into another. So in today's class we have seen about dimensions. Let me recap. In today's class we have seen about dimensions. So dimensions is nothing but it's a power of the fundamental unit which is used to represent the physical quantities. So we have seen some examples of dimensions. For area it is L square, for velocity it is length by time, for acceleration is length by time square. Moving on with force, which is ml T power minus 2, and for pressure it is ml power minus 1 and T power minus 2. Then we have solved a problem, or we have checked whether this equation is right by using dimensional analysis. So we took LHS, which is V square, and we know velocity it is length by time. So we got L square by T square. In the RHS terms we have V square V naught square plus 2AS. For velocity we will get the same answer, which is L square by T square. And 2 is a constant, so it has no dimensions. For acceleration we have length by time square, or L T power minus 2 dot L, which is for displacement. So we got the final answer as L square by T square in both LHS and RHS. Then finally we have seen its uses. The first one is it is used to test the correctness of the equation. Then it is used to derive the equation, and it is used to convert one system of unit into another. So that's all for now, and thanks for watching.